All right, so we've just started recording. This is lab 4 for EECS 281. I'm Milo. I've met some of you in office hours. I think the way that this has been previously working is we'll be giving a live lab, and we'll record the lab, and we'll be posting the recording. If there are questions, I will periodically check the Meet chat for questions, and I'll repeat the questions. And probably while I'm presenting, I may not be too attentive to the chat. See, I think that's it. And just one more time, we are recording this, so just keep that in mind. All right, and with that, I'm going to go ahead and start presenting. So today is May 18th, and we're going to talk about priority queues, heaps, and union find. So here are the announcements. We have lab 3 due 5/22, then 4 due the 29th. I believe those dates are correct. I just got them from Canvas. Then the major deadline that's soon coming is the May 26th deadline for project 2. Definitely keep an eye for that. You can keep on top of that. Then midterms coming up. Make sure to get any accommodations forms you need to the eecs281admin@umich.edu email. All right, here's probably a good point to stop. Any questions on this announcement, or these announcements, or anything logistical? Okay, I'm gonna move on then. All right, so here's our agenda. We'll talk about the previous lab written problem, then priority queues, then heap sort, followed by set union find. Then we'll do the handwritten problem. All right, so lab 3 handwritten. All right, so as a reminder what the question was, we had to check if two strings are anagrams, assuming they only contain lowercase letters and spaces. So one possible solution is we create something like a vector of chars. And well, first we realize that there's only 26 possible characters, and we can just keep track of the count of each letter frequency for the string in a vector of size 26. And so, this is similar to an interview problem, and now we're going to look at some code. So this is the instructor solution. Given two strings, create a vector of size 26, initialized to all zeros, and then iterate over the entire first string, counting all letters which are not space, and do the same for second string, except we decrement instead of increment. And if we ever have one of the values less than 0, then we can automatically escape because we know that there was more instances of a certain letter in the second string than the first string. And then as a final check, we make sure none of the counts are greater than 0. If they are, then there was a letter in the first string that wasn't in the second string, and so we return false. And if we have finished that loop, then all the counts are 0, and so we can return true. So I think one thing to note is, based off of a preliminary glance at some of the other solutions, a common thing to do would be iterate over, try to index into both string 1 and string 2 at the same time, and that can lead to out-of-bound indexing. It's not guaranteed S1 and S2 have the same length. And also on that note, S1 and S2 can have different lengths but still be anagrams, because S1 might have spaces, but S2 could not have spaces. So any questions on the solution to the previous lab's written problem? Oh, I see there's a question on the previous slide about times for the midterm. And I believe the current status of times for the midterm is it's to be determined. There will likely be multiple time slots, probably 2, but the exact logistics are still being worked out. So I'll give you guys a second or two to post anything in the chat if you are curious about, or if you have any questions about Lab 3 written problem. Oh, the lab slides should be posted. So the question was, is it possible to post the lab slides? Let me make sure they are posted. I think I posted them maybe half an hour ago. Maybe I just forgot to publish them. Oh, I just forgot to publish them. All right. There we go. They should be published now. All right. With that, I'll move on. If you can't reach the lab slides, please post in the chat again. All right. So now we'll talk about priority queues. So priority queues are an abstract container type, and the major specialty for priority queues is they have the ability to insert an item and remove an item with the largest key. There are a number of different possible implementations. One is the binary heap, pairing heap. There are a few others. You'll implement them in Part B of Project 2. I think there was priority queues was the topic for today's lecture. So you should be, have some good knowledge of priority queues. Then what does the STL have? The STL has a priority queue. It's implemented as binary heap, and it's got pretty nice interface. Push pop top empty size. Top empty size, all do what you would expect, similar to queue. So priority queue is part of queue. If you pound include queue, then you get priority queue. And with pop, it's log n time. It will remove the highest priority element. And with push, it will insert an element into the priority queue, and this also will take log n time. So here's the definition for priority queue. It's 3 template parameters. First being the type of each item stored in the priority queue. Second is the container for the priority queue. And the third is the comparator. The defaults for the last 2 are a vector of that type and and less than for that type. Then so in project 2 part A, you'll probably have to define a custom comparator, and so you'll likely use the template parameters to do this, to pass it to create a priority queue of this type. And let's say instead of less than, we want a greater. At the bottom, there is an example which uses greater, and so by default, with less than, it's going to be a min priority queue, and with greater than, with less than, it's going to be a max priority queue, so the max element is at the top. With greater, it's going to be a min priority queue, so the min element is at the top. Great. Okay, there were a few more questions. So there was a question about the previous lab written problem. So it was what does the decrement in the second for loop mean? So I'll go back. So the decrement in the second for loop is how we make sure that it's how we're keeping track of the character frequency of the second string. And so it's why at the end we can do the greater than or count greater than 0 to make sure every letter shows up exactly once. Or sorry, every letter shows up the same number of times. Then there was another question. Oh, someone responded. Yeah, I would agree. It says it's so that if the number of that letter in the second string matches the number of that letter in the first string, the count will end up being 0 at the end. Yeah, I would agree. All right. Any questions about the priority queues in the STL? All right, I'll move on. So we have a practice question. What if we wanted to find the kth largest element in an unsorted vector? I'll give you all 1 or 2 minutes to think about this. Feel free to put your thoughts in the chat, or if, after 1 or 2 minutes, if you want to share your thoughts, you can unmute yourself or whatever you want. All right, so I see there's been a few responses. One was that we could construct a PQ with less than, and then call pop k minus 1 times, and top element would be the kth largest. Yeah, that sounds pretty good. Then another thought was, what if we, let's see, what if we traverse the vector k times, throwing out the max each time that is found each time? Yeah, something like that might work. Or use merge sort. Yeah, I think that could work, and then just use the kth index. Any other comments? So I guess some thoughts are we want to do this efficiently, and so let's see. Approach 1 is add all the elements to a max heap, pop k times, and that's pretty good. We O of n plus k log n time and O of n space. So one thing to note is it's important to use the range constructor here. Otherwise, inserting every element will each take log n time, and you'll do that n time, so it'll be n log n time, where the range constructor by itself will just be O of n time. What about approach 2? Add the first k elements to a min heap, and then push and pop each of the remaining n minus k elements. And so the PQ is always of size k, or less than size k, or less than equal to. And so then at the end, we can figure out what the kth largest element of the vector is. And so then that's the top element, since it's a min heap. And this is essentially same runtime at O of n log k, and we use slightly less space, O of k space, which is pretty nice. All right, so then now we're going to talk about heaps and heap sort. So we have a binary heap, which is so a max binary heap is a binary tree such that each node has an equal or higher priority to the priority of both of its children, and it's complete. So all the levels of the heap are full except for the last, and the last level is filled from left to right. And binary heaps are used to create priority queues. This is something that you'll do in Project 2, Part B, and it's what's used for standard priority queue. All right, so now we have a practice question. Which of the following represents a min heap, and which is a max heap? Select all that apply. All right, I will create a straw poll and put a link in the chat. let's see. Okay, there should be a link in the chat, so please respond. All right, and there was a question, do the children in a heap have to have a lower priority than the parent? So if we go, I don't want to go back one slide yet. For a less than, if you have a less than comparator, then the children in a heap will have lower priority than the parent, because the parent is the greatest element, or the root is the greatest element, and so you can think about it that way. As you go down the tree, you lose priority. Right, and so there was a question about the previous practice problem. Is approach 1 O of n plus k log n for the same reason heapifies O of n? Yep. So with the range constructor, O of n is the complexity for the range constructor. So that's where the n it comes from for the O of n plus k log n. And then there's another question. Why is the range-based constructor reduce the time complexity? So if we didn't use the range constructor, we would do n pushes that each take log n time. And so that would be a n log n operation. However, since we're using, so n log n is going to be greater than n plus k log n, since n is greater than k. All right, I see there's been some responses. It seems like a pretty popular choice is A. So, yep, I would agree. A is a min heap, and then C and D are max heaps. And so I think one of the questions in the chat was providing useful insight. The left will be, so when we look at the children, there will be greater than, so for the min heap, the children will be greater than the parent. So here in A, 8 is greater than 1, and 4 is greater than 1. So far, so good. 9 and 12 are both greater than 8, and 11 and 7 are both greater than 4. So that makes it a min heap. For C and D, we want to do the opposite. The parent has to be greater than the children, or the children have to be less than the parent. So let's see, 10 and 6 are both less than 13. Then 8 and 7 are both less than 10. 4 and 2 are both less than 6. And let's see, 2 and 5 are both less than 8. 1 and minus 1 are both less than 7. And 0 is less than 4. See, I think my indexing is correct there. And similar for D, except now we have to think about it a little bit more because we have negative numbers. And so less than would be might be more analogous to distance, or when we think about negative numbers, we have to be more careful since one's intuition might be, or an immediate thought might be, well, this is more of a min heap because -1 is at the front and -9 is after it. But because of the way less than works, of course, -1 is greater than -9. All right. So any questions on this problem? All right. So there's been a few. Does the leftmost child have to be lower in priority than the children to its right, or does the priority at the same level not matter? So I think you're curious about what happens when it's equal. So I think it doesn't quite matter too much if it's equal. All that really matters is the parent has the key, or so in the case that it's less than, we'll have the max element at the top. And so, 45 is not less than 45. But even if it was, it would still be okay because you'd end up swapping 45 and 45. All right, and then the next question was, can you explain why B doesn't work? Yeah, sure. So let's see. I'll explain why B doesn't work for min heap. So I would agree 3 is less than 4, and 3 is also less than 5, so that's good. So the children of the root are fine. 4 is less than 7, and 4 is less than 12. 5 is less than 11 and 8. However, 6 is 7 is not less than 6. So that's where we have our issue. That breaks the heap invariant. 7 is greater than 6, but it should be less if we wanted to keep them in heap invariant. And let's see. All right, so I think now we'll move on. So let's talk about the implementation. So we have the tree-based on the left and the array-based on the right. And so, of course, the question is, in the tree-based, it's pretty straightforward to see the left and right children. In the array-based, it can be a little bit more challenging. And so, given a node at position I in the array, what's the index of i's parent, and what are the indices of i's 2 children? Any thoughts on what the indexes might be? I over 2? Yep, I agree. So I minus 1 over 2, and 2i plus 1 and 2i plus 2. So, for example, 19 is at index 1. So I think there was a comment I over 2. So if you were 1 indexed, then yeah, I would agree. But let's assume we're 0 indexed. So let's see, 19 is at index 1. So parent is at 0. Life's good. Think about 17. It's at index 3. 3 minus 1 is 2. 2 over 2 is 1, and its parent is 19. So life's good. And that's also seen on the left in the tree-based diagram. And the same logic works for the children left and right. So if we want to find the children of the root, I is 0, and so left child is 19, right child is 36. And if we wanted to find the right child of 36, we know from the tree-based it should be 1. So 36 is at index 2. 2 times 2 is 4, plus 2 is 6. And then index is 1, 2, 3, 4, 5. Index 6 is 1. All right. So how do we maintain the heap priority, heap property? So what if the priority of an item increases? We have this concept of fix up, or the fix up function. How does fix up work? We swap the altered node with its parent, moving up until either we've reached the root, or the parent with a larger, or we reach a parent with a larger or equal key. So with this in mind, what might be the complexity of fix up? Yeah, suppose friend nodes. Yep, I see there's a bunch of responses, log n, I would agree. It's O of number of levels in the heap, which is O of log n, and it's log n since heaps are complete, or are a complete tree. So what if the priority of an item decreases? Same idea. We have this function fixed down, and we swap the altered node with the greater of its children, moving down until we reach the bottom of the heap, or both children have the same or equal key. So what is the complexity of fix down? Again, on n nodes. Yeah, I would agree. Still log n. So how do we insert an element into the heap? Well, we would insert the new item at the bottom of the heap. We could do this by maybe just appending to the vector or whatever, depending on the representation of the heap. And then call fixup on the newly inserted item. And so calling fixup will move the item to its correct position within the heap. And what if we wanted to remove an item from the heap? Then we would remove the root by replacing it with the last element in the heap. Often this is like a swap and then maybe like a pop back or something like that. And then delete the last item in the heap. This is like the pop back. And then we call fix down on the element that's now in the root position. So since we call fix down, we'll move the item to the correct position within the heap. And so we have removed an item and we've kept the heap invariant. So I think just one thing to note is for this, when we remove, we are always removing the root element. All right, any questions on removing or inserting? Or fix down, fix up? So what is the position of the root after removing the root? So after we remove the root shouldn't be in the tree or in the heap. All right, I'll keep going on. So now we have a question. Consider an empty maximum priority queue. If we insert elements 14, 4, 5, 23, 9, 11, 2 into the heap, and then we remove the most extreme element twice, what are possible array representations of the heap? So I'll make another poll and I'll put it in the chat. All right, so I've seen 2 responses to the poll, so I'll give you all maybe 1 or 2 more minutes. All right, so I've just seen a bunch more responses. So the most popular response is D, and I would agree. I think D is the correct answer here. So when we think about if we have a max priority queue and we insert a bunch of elements and then remove them, I think the best way to show this would be a picture. So I'm going to try and do some drawing on the board, on the digital board. So let's see. I've got to, of course, log in on this iPad. Let's see if I can do that. So I'm going to try and share a Jamboard link in the chat to a new page. Let's see. All right, let's get the link. All right, let's see. Okay, I see someone joined. All right. So we've got this board, and we got a couple of elements. So 14, 4, 5, 23, 9, 11, and 2. So in this order, we're going to insert them into the max priority queue. All right, we know how to do that. For simplicity, I'm going to just use the tree representation, and then at the end, we'll take the tree and we'll convert it to the array representation. So we start off with 14, or I'm going to change color. So let's see, we've got 14, and then we do 4. All right, and so when we insert on the left, or we insert in the next level, and we always try to keep the tree complete. That's why we didn't add 4 to the right. All right, so now we got 5. So we also add 5. Yep. And next is 23. So when we insert, we add it to the end. All right, let me use another color here. So 23 is an interesting case since it's greater. So we add 23. And we have to call fix up. So we'll look at 23 and 4. 23 is greater. So 23 and 4 swap. And then we do the same with 14 and 23. And we see that 23 is greater. So we swap 14 and 23. All right, let me clean this up a little bit. Okay, so now we have 23, 14, 5, and 4 all inserted. So next element is 9. Same idea, you just add it at the farthest leftmost part. In theory, we would call fix up, but since 9 is less than 14, life's good, and we can move on. And now we do 11. So we add it to the bottom level at the leftmost position, so we add it here. And we call fix up, and so we compare 5 and 11, and 5 is less than 11, so we need to do a swap. So 11 goes here, 5 goes here, and then we do the same thing. We compare 23 and 11. 11 is less than 23, so we're done. And now we do 2, add it to the end. 11 is greater than 2, so we're done. We've added all of these elements into the heap. Next, we want to remove the most extreme element twice. So, let's see. We'll use black, or I'll use red. All right. So first we want to remove 23. So we remove 23 and 2, right? So 2, 23. So we did that swap. And then we remove 23. And now we've removed the most extreme element once. So we do, oh, sorry. We're not done quite yet. We still have to call fix down on 2. So we have to call fix down starting at 2. And so we look at the two children of 2, which are 14 and 11. So we need to swap it with one of them since it's less than both. But we have to make sure that we swap it with the max of the 2 elements. So we can't switch it with 11. Instead, so hypothetically, if we did swap it with 11, then we would have 11 as the root, and we would break the heap priority because 11 is less than 14. So maybe I can draw that out a little bit. So what it would look like is 11, 14, and 2. And since that breaks the heap priority, we can't do that. So let's see. Instead, we swap it with 14. And same idea, we swap, we call fix down, and we realize 14 is greater than both 4 and 9. Oh, I actually didn't swap it, did I? There we go, 14 and 2. And so we call fix down on 2, and 2 is less than both 4 and 9, so we swap it with the max, so we swap it with 9. All right, and so we've called fix down once, and we're done. So we call it one more time. We'll use another color, use green. So what do? We swap 14 with the last element, 5. Then we remove the last element, which is 14. And then we call fix down on 5. So we swap with the greatest element. We compare 5 and 9, there's less, and 5 and 11, and those are less. So we swap with the max of the 2 children. Max of 9 and 11 is 11, so we swap 5 and 11. And then we're done. We've removed the most extreme element twice, and so all we have to do now is convert the tree into the array representation. So what does it look like? 11, and 9, 5, 4, and 2. And that is option D. All right, so are there any questions about this practice question? All right. So I'm realizing that your question might be kind of long to type. So if you have a question, to stop me from moving on, maybe just type the question mark and then type out your full question. That way I know to wait. But for now, I'll move on. And I realized that the Jamboard is not being saved with the recording. So let's see. In the future, I will make sure to show the Jamboard in the recording. So next time we use it. All right. I'll also include the Jamboard link when on Piazza or whatever, so people have access to it. All right. So make heap. So heapify idea 1. So we build a heap from scratch. We could just start with an empty heap and then insert item 1 by 1. And so, like we talked about earlier, this is n operations that are each log n. So it's O of n log n, right? Each one is log n. We do it n times, and n log n. What if we did something slightly better? What if we initialize the heap's underlying array to the unsorted array? And then method 1 is we repeatedly call fix up, starting from the top of the array and moving down. And this is equivalent to repeatedly inserting items into the heap. So based off of that, we already know it's going to be the same complexity, n log n. But what if we did method 2, which is we repeatedly call fix down, starting from the bottom of the heap and moving up. So this is the equivalent to making small heaps and gradually merging them together. And so which approach is better? Kind of gave it away. Method 2. So we call fix down starting from the bottom. And now we'll have some nice animation. So here is the tree, or the underlying vector represented as a tree. So, right, the key idea is the complexity of fixing the position of one item is O, the depth of the item. And we need to fix every item to ensure it's in the right place. So this is the fix up implementation where it's n log n, right? So we have a bunch of different nodes at different depths, and so we take the sum, and so it's 1 plus 2 plus 8, and so on and so forth, summation of log n times n over 2, and this ends up being O of n log n. So the key insight is we spend a lot of time we're doing the most expensive operation, the log n operation, on the most common root, on the most common case, right? So the most common case is we're at the bottom, or we're at the bottom 2 levels. And by calling fix up, then fix up on those nodes is expensive. So what if we did the other option, which is fix down, the more efficient option? Well, we kind of invert it, right? So yeah, the height of the root is log n. So for the root, we're going to be doing a log n operation, but the common case is the bottom nodes, and those end up being, very, very fast, O of 1, or log of n, the height of the leaves or almost leaves is very small. So we do the cheaper operation is more frequent here, and the more expensive operation is less frequent. So it has better complexity, and right, is the summation of these items is n times a bunch of 1/2s, and so 1/2 plus 2/4, so on and so forth, and this becomes just O of n. And so it's O of n instead of O of n log n, which is getting back to what we talked about earlier, why the range constructor, you should try to use it as much as possible, because it's going to be more efficient than inserting n elements into the priority queue. So are there any questions about fix down versus fix up in the range constructor and why we want to use the range constructor? What is the syntax for the range constructor? Yeah, sure. Let's see. I will put it in the Jamboard. So, see. I'll go to the next slide. Hopefully, can people in the Google Meet see the Jamboard directly? Yep. Okay. Great. So now it should be in the recording. So sorry about that earlier. Anyways, so what if we wanted to use the range constructor? Let's say we have some vector of ints. We'll call it vec. And we insert a bunch of elements. And then we want to create a priority queue. So we have a priority queue. And the type is int. And the second parameter is the container. So we'll have a vector of type int. I'm going to make this multiple lines. I think it'll be a little bit easier to read. And the last one is our custom comparator. So comp. And now we declare the actual object. We'll call it PQ. And to use the range constructor, we pass iterators to the container that we're iterating over. So we'll do vec.begin and vec.end. All right. So now PQ is constructed using the range constructor. All right. So then let's see, what other questions are there? So fix up starts from the root, fix down starts from the leaves of the tree. Am I understanding that correctly? So in either approach, we need to call either fix up or fix down on every node. In the fix up strategy, then we start at the base of the tree. And in the fix down strategy, or sorry, I misspoke. In the fix up strategy, we start from the root, and in the fix down strategy, we start from the leaves. Yep, you're correct. Let's see what else is there. Yep. Okay. No other questions. All right. So I think now we will move on to the next. All right. So now we got some animation. So let's see, we have this example, and so starting with fixed down, start at 5, we'll call fixed down on 5, 5's a leaf, so we're done. And then we go to 3, 3 is a leaf, so we're done. 13, 13 is a leaf, so we're done. Then we do 8, 8 is a leaf, so we're done. 27, 27 is a leaf, so fixed down on 27, nothing to do. Then we go to 40. We call fix down on 40, and 40 is greater than 5, so we move on. Then we call fix down on 1. 1 is less than 13, and 1 is less than 3, so we swap 1 and 13 since 13 is the greater element. Then we move on to 16, And 16 is less than 27 and 16 is less than 8. So we swap it with the max. And so we swap 27 and 16. And then we're done for 16. And we go to 24. Calling fixed down on 24. 24 is greater than 13, but 24 is less than 40. So we swap 24 and 40. And then we compare 24 and 5. 24 is greater than 5, so we move on. And so now we have the last element, the root, and so we call fixed down on 3. And let's see, fixed down on 3. 3 is less. 3 is greater than 40. Or sorry, 3 is less than 40, and 3 is also less than 27. So we swap 3 with the max 40 and 27. So we swap 3 and 40. Then we compare 3 with 13. 3 is less than 13, and 3 is less than 24. So we swap it with the max of 13 and 24. And again, 3 is less than 5. So we swap 3 and 5. And then we're done. So any questions on the fixed down example? Why isn't it nlogn? Right. So I'm going to go back to this slide. This slide here. So here the summation is each of their heights times the number of times we do it. So the 1 times n over 2 is let's see, n over 2. So max number of nodes and the log n height. Right. So we do a summation of 1 times n over 2 plus 2 times n over 4 plus 3 times n over 8, all the way to the more general formula, which is log base 2 of n times n over 2 to the log base 2 of n. The way we arrive at that formula is log n is the complexity of each fixed down, and n over 2 to the log n is the number of nodes that we, let's see, the number of nodes that we do at this operation for. If I'm not mistaken, let's see, log, let's see, is that right? Log 2 of n. Let's see, log 2 of n. Yeah, okay. Yep. So here it's slightly confusing because n is our indexing variable. Or no, n is not our indexing variable. Log base 2 of n. 1 plus 2 is 3 plus 4. All right, let's see. So 1 times n over 2. 1 times n over 2 is, I see, okay. So here the 1 times n over 2 is because the number of leaf nodes is n over 2, and each of those will take a fixed down that costs 1. So not exactly what we have in the chart there. It's height plus 1. So 1 times n over 2 is accounting for all the leaves, and then 2 times n over 4 is accounting for everything that's 1 level above the leaves, and so on and so forth. 3 levels above the leaf, as there's n over 8 of them. Then we take out the n from each of these, and this is the summation of, let's see, 1/2 plus 1/2 over 3/8, which is 2, and let's see, then it's just O of n. Yeah, okay. So does that answer the question on why it's n rather than nlogn? I guess the analysis is a little bit more clever, which allows us to do O of n rather than O of nlogn. All right, any other questions? So there was an insight that it makes sense that it's O of n because it's more nodes are at the bottom. Yeah, I would agree. All right, so I'm going to move on. All right, so we got a summary. Calling fix down, starting from the bottom, has complexity of n. Calling fix up has complexity, calling fix up starting from the top has complexity n log n. And as mentioned, the key ideas are the bottom levels of the heap has the greatest number of items. So fix down on these items would require almost no work, and so since they're already in the correct position. And in fact, when you do the fix down strategy, you only need to consider the nodes before index n over 2, or ceiling of n over 2. So since everything after that is already a leaf. So really, the range constructor only needs to consider 0 to n over 2, backwards, of course. And so calling fix up on these same items would require O of log n work for each item. And since there are log n levels, this ends up being n log n. So fix down method is more efficient. So we are effectively building many small heaps and merge them by adding new nodes, which costs O log n. And it's mostly on very small heaps, so it's limiting the work. All right, so now we're going to talk about heap sort. So we can use a binary heap to sort items. The idea is we identify the largest item, move it to the end, find the next element, move it to the end, so on and so forth. And we start with building a heap using make heap or heapify, and then we remove items from the heap one at a time to get them in sorted order. So the initial range constructor allows us to do the heapify process in O of n time. Then each removal is log n time. And since we do the removal n times, it becomes n log n. And so overall, the complexity is O of n log n. So that's the complexity of removal plus fix down, since it dominates the O of n complexity for heapify. So I believe one can show that any comparison-based sorting algorithm has time complexity at least O of n log n. There are some sorting algorithms that do not use the typical comparator, maybe something like radix sort, and the complexities vary a little bit, but unsurprisingly, heap sort is no better than the other sorting approaches that we've seen. All right, so here's an example. We have this container, which is unsorted, and we're going to call heapify on it. And so we want to find the largest element, so we're going to move it to the end. First step is heapify this into a max heap. So we look at 34 and 46. So we don't even need to consider 34, 46, and 89 because they're leaves. So the first element we consider is 17. 17 is not less than 46. 17 is less than 46. So we swap 17 and 46. We swap it with 46 since 46 is the max of 46 and 34. And then we look at 46 and 53. 46 is less than 53, so we move on. And then we call fix down on 53. And 53 is less than 89, so we swap 89 and 53. So now we're done doing heapify, and we can remove the largest element. So 89 is the largest element at the top of the heap, And so we move it to the end, and so we swap 34 and 89. Then we remove 89. And so no 89 is in the correct position here. And so we don't want to move it, so we'll just ignore the fact that this exists. And so we still have to call fix down on 34. So, right, we have to keep the max heap invariant. So 34 is less than 46 and 34 is less than 53. So we swap it with 53 since 53 is greater than 46. And then we're done for calling fix down. And so the heap is valid. And the next largest element is 53. So we move it to the end, swap 53 and 17. And as you see in the array representation, 53 is now at the end. And we continue doing this until we have to call fix down on 17. And so we'll swap 17 and 46. And then, this heap is valid. Let's see, yep, 17 and 46. And so we have to, the next item to do is pop the top element of the heap. So we move 46 to the end. So we swap 46 and 34. And 46 is in the correct position in the array. And so now we just have the heap 34 and 17. So we want to pop 34, so we swap 34 and 17. And we remove 34 from the heap, and all we have left is 17. And so we pop that element, and we're done. So now we have the sorted elements 17 through 89. All right. And so are there any questions about priority queues or heap sort? All right, I don't see any questions. There's a question. So when we remove from the heap, is that popping? Yes. Yep. Exactly. So std priority queue : pop. And then is our array empty? Is our array empty? So the underlying data structure that holds all of our elements would be empty. Yes. So there are different ways to do this. One is to use an auxiliary data, use two separate containers, one that holds the elements that you get from the top, and you just push those back in. The other way to do it is in place. And so here, in theory, the array representation could be the same as what we're using for the heap itself. Let's see. In a way, our array is empty because the array part that's representing our priority queue or our heap is empty, but the actual array itself is still there, still holding all of the elements. And so are there any reasons you wouldn't want to do the heap sort in place? Yep. So like, as I mentioned, heap sort can be done in place. Let's see, is there a reason you don't want to do heap sort in place? I can't really think of a good reason not to do heap sort in place. Yeah, it seems like a pretty reasonable thing to do in place. I suppose maybe if your elements were exceedingly large, you might want to do an indirect heap sort, in which case, I don't know, you can still do it in place. So yeah, it's a pretty reasonable thing to do it in place. I can't think of any examples, but they probably exist. All right, so I guess now we'll move on to set and union find. So what is a set? It's a collection of objects, and you can only check one thing. And so, right, is the object contained in the set is what a set might be useful for, and it's the only thing we can check. So the set, here are some examples. In the first, 1, 2, 3 set, you've probably seen these before, and maybe equals to a 3, or maybe a math course, or math 465, I think is the other prereq that we allow. And so let's see, in the next item, 1, 1, 1, 2, 3, 4 ones and then a 2 and a 3 is going to be the same as 1, 2, 3. So all of these sets are the same. The representation, or the order in which they appear in this notation doesn't matter, and the number of times it appears doesn't matter. It's as though it only appears once. And there's also the empty set, which is the set containing nothing. So then we have some set operations. We can union, which is combining the two sets. So set of all elements that are members of A or B, intersection, set of all objects that are members of A and B, and then the set difference, which is the set of all objects that are members of A but not members of B. All right, so we'll do some examples. What is the union? What is the intersection? What's the difference? So here the union is 1, 2, 3, 5. Since the distinct elements are 1, 2, 3, 5 of A and B. And so then what's the intersection? 1 and 3. So 1 is in both A and B. 2 is not in A and B, so it's not in the intersection. 3 is in A and B, so it's in the intersection. 5 is not in A, so it's not in the intersection. Then A minus B, since 1 is in both A and B, it gets removed. And so 1 is not in the difference. 2 is in A, but it's not in B, so it's in the difference. And 3 is in A, but not in B. Or sorry, 3 is in A and in B, so it gets removed. We don't really need to concern ourselves with 5, since 5 is not in A. All right, so more set operation notes. A sorted vector is a good implementation for a set that doesn't need to insert or erase elements often. And you can use binary search to check for membership. For a set that needs to insert or erase elements often, we'll see an effective implementation later after the midterm. And they can do both of these operations in O of 1 with high probability. And so practice, how would you implement the following operations on 2 sorted input vectors and 1 output vector? So if we want to do union, we want to do intersection, we want to do set difference. I think set difference here is pretty common, or is an example pre-response question. When we start to prep or when we start to release more resources to prep for the midterm, I think one of the written questions is set difference of 2 sorted input vectors. So I'll give you a minute or 2 to think about those. So there was a question, hash tables? Yes, the answer is yes. The item we will talk about later is hash tables. All right, so now we'll talk about how to do union intersection set difference. So union, we iterate over each vector, push the lower element to the output vector, and increment its iterator. And if the elements are the same, only push 1 and increment both. By doing so, we can avoid duplication. And so for intersection, similar idea. We want to iterate over. And if the elements are the same, push 1 to the vector and increment both. But if the elements are not the same, then we don't push. We just increment the iterator to the lower element. Then set difference. Again, pretty similar idea. We iterate over them. And the cases we consider are if the elements are the same, then we increment both because we don't want to include that in the difference. And then if A's element compares lower, we push it to the output vector. And we increment the iterator of the lower element, or we increment the iterator of the container pointing which currently has the lower element. And we have to do this in case the next element matches the higher element. So I'll keep going. So how do we know if two things are in the same group? Well, I guess this is pretty different. So are there any questions on how we do union, intersection, and set difference? All right, I guess we'll move on. So now we have this same, how do we know if two things are in the same group? So here we've represented A and B as two sets that are connected, kind of like graphs. And the question is, of course, are these two elements in the same group? So what if we add, so okay, before the answer is no, but then what if we add this connection? Then the answer is yes. They're both in the same group, which is the union of the two. And so now we'll talk about union find. I don't think union find has been discussed yet in lecture. So this is going to be some new content, but it will get covered in lecture, probably on Wednesday. Let's see, maybe Wednesday. Well, it'll be covered soon, I believe. All right, so union find, or just disjoint set, it's a data structure for managing disjoint sets. It's a way to determine whether or not two elements are in the same group for any arbitrary number of groups. So a traditional set won't work for this task. We want to quickly check whether the known elements are in the same set, not check whether or not any element is part of a single set. So arbitrary number of sets, right? Then we so it's implemented using an array of integers and two functions, union and find. So each element has a representative, with air quotes, a representative that helps identify the group they're in. So kind of before, right, in this diagram, here representative of A would be 1 and representative of B would be 2. And union will make the representative of two elements the same and all of the representatives the same. All the representatives of those two items in the groups the same. So more precisely, if X and Y are in different groups, their groups will be combined into a larger group, and we'll do that combining by changing representatives. And find of X will return the representative of the group that X belongs to. So a possible implementation is hold a representative for each item X, but then we can scan through the entire vector to update representatives on a union. And this can be fairly costly. So we need to be a little bit more clever in our union. And so can we encode a union while only updating one representative? So that's the question. And so now we've got some examples. How do we tell if two people are citizens of the same country? We check if they have the same leader. So kind of like we have this sort of tree representation and we follow it up. So right, how do we find someone's leader? We walk up the tree until we find someone whose leader is themselves. So that's our basic idea of how we're going to use representatives. And so let's say we had the bottom element of we were the bottom person of the left, then we can find the representative. And we could do the same for someone on the right, and we would see that the representatives are not the same. So suppose we have two groups. How do we combine these groups? After combining, all elements must have the same leader. So we want to modify as few nodes as possible for efficiency's sake. And so in the hypothetical example, suppose the US and Canada merge, all the Canadians gain American citizenship. So how do we modify the diagram on the previous slide to reflect this? Well, we can just have the leader of the previous leader of Canada to now have the leader of the US. All right, so with that in mind, how can we make this even faster? Or okay, I guess maybe before we get to path compression, does the idea of using representatives make sense? Does how we might do find make sense? And does how we might do union make sense? Are there any questions about those? Yes. As a Canadian, so there's a comment which is, as a Canadian, I'm miffed about this. Yeah, I see how someone might be miffed about this. I'll bring it up and we'll consider changing the slide so it's maybe less political. Maybe we can do more abstract groups. There was a comment saying, just joking. All right. So now we'll talk about how to make it slightly faster. So we can do path compression. So the issue is we can still have this sort of stick. So if we union a bunch of elements together, we could create this worst case scenario where the one is the leader, is the representative, but and then representative 2 is 1, and representative 3 is 2, and so we have this long chain. I think there's a better diagram later in these slides. First of all, so how do we prevent this long stick? We can use path compression. And so suppose we call find on multiple element, on an element multiple times. It takes work to move up the tree to find this representative, especially if we have to move up multiple levels. But as long as the representative is the same, all the elements along our path to the leader will have the same representative. And so we don't have to do all this work over again if find is called on an element multiple times. So with this in mind, our solution is every time we call find on an element, we move the element closer to its representative. So we update its representative with the one that's closer to the representative, the furthest, the base representative. And by doing this, we can reduce the work we have to do a find again. And so this concept is path compression because we're taking this long path, then we're making it shorter. So here's a little bit more code to go along with this idea. Every time we call find an element, we move the element closer, and this can reduce work. As seen here, so if the representative of x is x, then that's the base, so we just return x. And otherwise, we can do a recursive call and update this x's representative. So every time we call find on the circle person, we move up the tree to find the ultimate representative. However, after calling find once, we know that all purple people have the same leader. And so we want to repeat we don't want to repeat this work over again, so we can compress this long path by updating all of the representatives. So now all of the we've removed a bunch of indirection, and each purple person's representative points directly to the leader. And so this will help prevent the tree from being too tall or having too much depth. And so how does this look as we implement it? So we have this array representation, and initially all of them are parts of different groups. And so 5 separate groups, and every representative is different, and nothing is connected. So now let's say we want to connect stuff. So we union 3 and 4. All right, that's easy. We can just change the representative of 4. So we've changed 4 from being the value at 4 from being 4 to now be 3. So life's good, and our data structure is looking fine. We can still do find, and so if we did find of 4, we would get the value 3. So the representative of 4 is 3. And what if we did the same thing? We union 2 and 3. So 3's representative is now 2. And so 2 is the ultimate representative of the group. So notice how 2's representative is itself, but 3 and 4's are not themselves. And also, it's worth noting that 4's representative is still 3. So when we actually want to do find of 4, we're going to have to look at 3 and then look at 2. So I think there's, right. So find of 4 without path compression, 4 looks at its representative, 3 looks at its representative 2, and 2 is its own representative. So the representative of 4 is 2. And so this is how find would work without path compression. We just iterate over, keep updating x until we find a representative, which is itself. Find in the worst case, so if we have n elements, then we have this long chain, 4 to 3, 3 to 2, 2 to 1, 1 to 0, and 0 to 0. And so since we don't do path compression, it's O of n. And so every time we call find of 4 is O of n process, right? And so we've talked about how to fix this. We use path compression. So find of 4, after the first find of 4, or so the first call to find of 4 is O of n. We can't get around that. But the second call, we've updated all of the representatives to be 0, and so it's going to be O of 1. And we've also updated the representatives of 2 and 3, so those are faster now too. And so this is find with path compression. This is a pretty verbose solution. There is a little bit of a nicer solution. But if you want to know the nicer solution, we can talk about it after, at the end of the lab. All right, and then find of x in the average case without path compression, log n time. Log n is not really what we want to talk about here. So this is with the assumption that the height of the tree is log n. It's, I guess, better thought of as O of the path length. And yeah, this long block of text is essentially saying that the average path for this tree structure from the starting element to the ultimate representative is logarithmic. And with path compression complexity defined, it becomes amortized Ackermann of n, or the inverse Ackermann of n, which grows very slowly. And this is better in both the average and worst case. So it's often a good idea to use path compression. And so then union, what does that process look like? And so we do find of x on any member of, it will return the ultimate representative. And we can find the ultimate representative of both and have one representative point to the other, i.e. here, if we wanted to union 1 and 4, reps of find of 4 is find of 1. So we'll have updated the representative of 4. So our union is pretty straightforward. It just calls find and updates the representative. And as noted here, you can't call the function union, since union is a reserved word. I think a typical solution is set union or just underscore union. And so some complexity analysis. So it depends on whether or not you use path compression, but if you use path compression, then union becomes amortized O of inverse Ackermann of n, which is approximately O of 1. And so you should use path compression, and your decision to use path compression does not change the functionality of union and find. Find still returns the ultimate representative. it will just take longer without path compression. And finally, as a note, this has several applications, counting the number of connected components in a graph, and that is the autograder portion of this lab. And seeing if connecting two nodes in a graph form a cycle, Krustal's algorithm. Yep, it's also useful there. All right. So putting it all together, we have union find with a union and with a find and a set union function. So when you're doing the lab, the connected components lab for or when you're doing the autograder section for lab 4, which is connected components, number of connected components, it's probably going to be a good idea to come back to these slides and use some of the code here. All right, so now we've reached the handwritten problem. Given n ropes, find the minimum possible count of connecting ropes, where the cost of connecting 2 ropes is the sum of their lengths. So, for example, consider 4 ropes of length 10, 5, 8, and 11. Minimum cost to join them is 68. And then walk through of those, and total cost, right, 68. So at this point, I'm going to well, are there any questions with content covered in the lab? Anything about union find? Well, yeah, I guess I didn't ask if there were any questions about union find. So now is a good time to ask questions about union find. Is this similar to ancestor? I'm not sure I understand what is meant by ancestor. So if you mean representative, is representative similar to ancestor? Again, I still don't think I understand what is meant by ancestor. All right, I'll give a minute or two to see if there are any more questions. All right, so are there any questions about the handwritten problem? I believe I published the starter files to Canvas, so they should be there. All right, and with that, I'm going to stop the recording. Let's see.